So thank you for the introduction, and thank you all for coming here today to talk to me about the work that I've been doing. As John said, as part of my PhD research, I'm excited to share this with you today. So just to sort of frame the discussion today, I want to start with a few simple questions. We all have likely heard of the San Andreas Fault in Southern California, and it's obviously a large seismic hazard. But it's not the only seismic hazard. So where does this hazard in Southern California come from? What are the other contributors? The San Jacinto is one of them. And today I want to talk a little bit about microseismicity in the fault zone and ask the question, what can this microseismicity tell us about macroseismicity? What constraints can we impose on the next big earthquake by looking at the small earthquakes? So here's a quick outline of just the talk today, just so you know where we're going. I'm going to start by giving you a little bit of background information, set the sort of regional context, and give you a little bit of insight into some of the work that's already been done in Southern California, particularly the work that's relevant to what we're doing now. So here is an overview map of the plate boundary region in Southern California, and I've indicated a few select cities to orient yourselves. Here's Los Angeles and San Diego, Palm Springs for anybody who's been to the SCEC meeting, and the town of Anza. It's a small town here on the San Jacinto Fault, but it's a prominent marker. So I just want to draw your attention to the town of Anza there. By way of nomenclature, these are the major faults in Southern California. We have the San Andreas, which runs the length of Southern California, north to the San Francisco Bay Area, and it's nominally the plate boundary. The Garlock Fault is the primary conjugate fault in the plate boundary region, running approximately northeast to southwest. And subtended between these two is the Eastern California Shear Zone, a broad zone of distributed deformation. Here in El Cajon Pass, the San Andreas Fault bifurcates and continues to the east of the Salton Sea, and as the San Jacinto, parallel to the San Andreas. Seaward of the San Jacinto is the Elsinore Fault, and it's also running parallel to the San Andreas and San Jacinto. So the Southern California Seismic Network has been the authoritative agency for monitoring earthquake activity in Southern California since 1932, and they currently operate 414 seismic stations. In addition to these 414 stations that they operate, they acquire data from over 1,200 other stations. These 1,200 additional stations are largely strong motion accelerometers located in major urban centers like downtown Los Angeles. And here I'm showing the location of 337 broadband seismometers that contribute data to the SCSN. And so I'm only showing broadband seismometers here because they're the type of instrument that are particularly sensitive to the signals from small earthquakes that we're interested in looking at. So it's not really enough just to run a seismic network. The SCSN has also employed analysts, trained analysts since its inception, who look at the data and produce a catalog of earthquake locations. And so they routinely publish a catalog of regional seismicity. This is looking at seismicity in the region going back as far as 1932. And there's about 700,000 earthquakes in this time period. This paper by Hutton, Vosner, and Hoxson gave a nice summary of the history of the SCSN. In 2012, a series of studies culminated in this 2012 paper by Hoxson, Yang, and Shear, where they relocated seismicity from the SCSN catalog using a double difference algorithm. So this is based on differential arrival times that are measured by cross-correlating waveforms, and it produces high precision relative event locations. So they take the SCSN catalog, they cross-correlate waveforms to make these precise differential arrival time measurements, and then relocate the catalog to produce this new relocated catalog going back to 1981. There's about 600,000 earthquakes in this catalog. So those are the two main regional catalogs that exist in the region. Here is our study region, and our focus area is outlined in the white dashed rectangle. The San Jacinto fault zone is the most seismically active fault system in Southern California. It's more active than the San Andreas. It's ruptured in 15 magnitude 7 and greater earthquakes in the past 4,000 years. There's paleoseismic evidence for these. It accommodates about 10 to 21 millimeters per year of the plate motion. This is, depending on the estimate, this is about half of the plate motion, with the San Andreas being the other major contributor to accommodating this plate motion. And there's about 25 kilometers of accumulated slip on the San Jacinto compared to the hundreds of kilometers on the San Andreas. These are the major faults in the study area. So again, we have the San Andreas here to the northeast. We have the Elsinore to the southwest, and the San Jacinto running through the center. The Clark trace is the primary fault trace running the length of the region. The Hot Springs fault is displaced to the northeast a little bit from the main trace. It's offset by about 10 kilometers. And this region surrounding the Hot Springs fault is known as the Hot Springs area. I'll be touching on that a little bit. Town of Anza is here, and it's associated with a gap in microseismicity known as the Anza seismic gap. And then here, to the southeast of Anza, we have the Trifurcation area, which is so named because the Clark fault trifurcates into the Buck Ridge to the northeast, the Coyote Creek fault to the southwest, and the Clark fault continuing through the center. So that's a little bit of the background information. And so I want to touch briefly on where I think there's a gap in our knowledge and how we can close that gap. So this is just looking at a frequency magnitude distribution for data from the Hoxton et al. Catalog inside our focus region during the period that we analyzed between 2008 and 2016. And essentially, the point here is that the catalog is complete above magnitude 0.98. So if we can recover information in this green area here, where the catalog is incomplete, we can stand to gain new knowledge about the fault zone. So some potential questions that we can try to answer: when and where do these smaller events occur? Do they reveal any seismicity pattern anomalies preceding significant events in the San Jacinto? And what kind of information can they give us on mechanical and geometrical properties of the fault zone? So now I'm going to just discuss some of the work that we've done in the area. The first question that's logical to ask is, why do you think that you can do better than the SCSN and Hoxton, Yang, and Shear? They're great scientists, and it's a great agency. The answer to that is fairly simple, because we have more data. So SCSN is responsible for monitoring the entire Southern California region. And so they omit data from certain seismic stations that make negligible difference for monitoring regional seismicity. So here I'm showing the stations that we use in common with SCSN in red. And in cyan, I'm showing about 35 stations that we use that they do not use. So by using this additional data, we expect to be able to detect and locate more earthquakes than the SCSN. So here is a timeline of showing the network history. The important thing to notice here is the black dash line, which is the number of stations that we use as a function of time, scaled according to the vertical axis on the right here. And you can see it increases throughout essentially the entirety of our study period between 2008 and the end of 2016. And particularly relevant to our study is this purple curve here. So each of these colored curves represents stations coming from a particular network. And this purple curve is the San Jacinto Fault Zone Experiment Network, which began to be deployed in 2010 and really ramped up in late 2011. And so those stations are particularly important for this study. So the idea is we take this additional data and we want to process it all automatically to derive a new earthquake catalog. And so a large component of this work was developing a processing procedure to do that. We begin with raw waveform data, which is different than many other techniques that are popular today, like template matching. This does not require any a priori information. We just need the raw waveforms and the network metadata. The first thing that we do, actually I should say that I've divided the processing procedure into 3 phases here, where the first phase is detecting and locating events individually. And this produces a catalog that is comparable categorically to the SCSN catalog. So these are absolute event locations we get out of phase 1. Phase 2 is a relocation step where we produce a catalog that's comparable to the Hawkson et al. Relocated catalog. And then finally in phase 3, we apply some post-processing and quality control. We calculate event sizes and discard any poorly constrained or spurious solutions. The very first thing we do is run a P-wave detector. It's a simple STA-LTA algorithm to detect P-waves. And each of those detected P-waves triggers a search for the corresponding S-wave using a multi-step algorithm that first derives a polarizing filter to suppress compressional wave energy and allow shear wave energy to pass through, before running a series of statistical detectors to make the arrival time pick. Once we have these P and S wave detections, we attempt to associate them with unique earthquake events. So we perform a grid search procedure where we take a grid node as a hypothetical location and calculate synthetic travel times using a 1D velocity model and see if there are detections at least 5 unique stations that are coherent with a potential source location. So if we find such a source location, we associate those detections with that event, and it's an iterative procedure. So we associate detections with events, and then use a probabilistic, nonlinear, global search location inversion to account for 3-dimensional velocity structure when we're locating the events individually. And so for this, we're using 3-dimensional velocity model that was produced by Hung Jian in 2016, and we combine it with the community velocity model from the Southern California Earthquake Center to produce a hybrid model that is high resolution inside the core fault zone, and then has accurate resolution in the fringes of our study area where Hung Jian's high resolution model is not as well constrained. Once we have absolute event locations, we cross-correlate each event, the waveforms from each event, with each of its 200 nearest neighbors to measure differential arrival times, which we use with the GROW+ double difference algorithm to relocate the events and produce high precision relative event locations. Once we have our high precision relative event locations, we can calculate local magnitudes and seismic potencies, scalar potencies, which are scaled and reported as moment magnitudes. And finally, we apply some quality control metrics to discard spurious and poorly constrained solutions. I don't want to go into too many of the details of parameters, but just to give you a flavor of the signals that we're after here, I'm showing the parameters that we use for running the STA-LTA algorithm to detect P waves. And the important thing that I want to point out is the length of the short-term average window length. A conventional value for this for a standard operating network would be something like 1 second. And so this is a really short window, an order of magnitude shorter. And we use this because it's highly sensitive to the short duration impulsive signals coming from the microseismic earthquakes that we're interested in. These values are sample rate dependent. So we have data coming in at different sample rates, and for 80 samples per second, this window only has 8 data samples in it. So, we have to relax this criteria a little bit for the lower sample per rate data. Most of the data we use is 100 samples per second and greater. This isn't particularly important, but we use a particular method for estimating the level of catalog completeness. Basically, it's composed of an ideal frequency magnitude distribution, Gutenberg-Richter statistics, modulated by this Gaussian CDF that represents network sensitivity, which says that for magnitude 3, 100% of events are detected, but at magnitude 0, something like 10% of events are detected. And so where this blue curve, which is the best fitting model, deviates from this orange line is what we call the level of catalog completeness. Okay, so what do we get when we take this automated processing procedure and apply it to data from our aggregate network between 2008 and 2016? We get a catalog of, depending on how exactly we cut it, about 108,000 earthquakes. So this is seismicity in the San Jacinto fault zone region. And there's a few interesting features that I want to point out here. The first one is in the Hot Springs area. So we have the Hot Springs fault to the northeast. We have the Clark fault to the southwest. And the seismicity in this region is predominantly below about 13 kilometers. It's distributed in this sort of elongate volume that trends parallel to the surface trace and is located between the Clark and the Hot Springs faults. So the seismicity at depth does not correlate directly with the surface traces of the faults. Here is the Anza seismic gap at the northwest edge of the Trifurcation area. There's a sort of pocket of seismicity here in the seismic gap, but on either edge there is a area that's devoid of seismicity. We see some off-fault seismicity that is shallow and forms structures that are nominally perpendicular to the fault zone. And then here in the Trifurcation region, we have shallow seismicity between 5 and 10 kilometers that is distributed with a trend that is perpendicular to the surface trace of the faults. Located between the Clark and Buck Ridge faults, we have this deeper seismicity here that is similar in its character to the seismicity in the Hot Springs region. Okay, just to sort of give you some general features of the catalog. These are the detection counts at different stages in the processing. So, but we run the P-wave detector and detect over 11 million P-waves. Each of these 11 million P-waves triggers a search for the corresponding S-wave, of which we find a little over 4 million. At this point, we have not yet associated any of these arrivals with events, so there are 0 events in the catalog. We then run our association procedure, and of these 11.3 million P-waves, 2.1 of them are successfully associated with an event. So it's important to note that the majority of these, well, not the majority, a large number of these may not be from genuine seismic sources. Anybody who stubs their toe on a seismometer is going to create a signal that can easily trip the STA LTA. So there's all sorts of non-seismic sources creating these P waves. So we run the association. We associate about 2 million P waves, 1.6 million S waves with 160,000 different events. We then apply quality control and discard close to 52,000 of these events as either being poorly constrained or spurious. And so the quality control metrics, one of the main, most important ones is we require that the absolute location error on every event be less than 3 kilometers. So there are no events there should be no events with a location error greater than 3 kilometers. And that value is estimated by the absolute location.
Is that
algorithm.
apply to depth too?
Yeah, so I'll show you a figure on the distribution of errors, but yes, it applies to both horizontal and vertical components. And then finally, of these 108,000 events that we retain in the catalog, 102,000 of them are relocated using the double difference algorithm. Okay, so here is a map of location errors, and there are 2 things that are worth noting here. So on the left is horizontal location error, on the right is vertical location error. As I said, everything with error greater than 3 kilometers has been discarded. So that's the maximum error we'll see. I'm showing you the median in each grid cell, the median location error. And the locations are well constrained in both the horizontal and vertical inside our focus region. The errors are nominally between 1 to 1.5 kilometers. Outside the focus region, however, the vertical uncertainty rapidly increases, and we don't observe the same rapid increase in the horizontal location error. So what's particularly interesting about this to me is conventional seismological wisdom will say that the horizontal error is always smaller than the vertical. But what we're observing here is that the vertical error is in fact smaller than the horizontal error inside the focus region of our study. So this likely has to do with the fact that the seismicity is quite deep and the station density is quite high. And so where you have a combination of deep seismicity with dense station coverage and accurate S-wave picks, we have stronger constraint on the event depth.
Do you have any deep borehole stations, or are these all surface stations?
There are a few deep borehole stations, and when I say deep, I mean like 50 to 250 meters,
Okay.
coming from the Plate Boundary Observatory Network.
These are the absolute location errors, just formal errors with
Yeah, so the particular software is called non-Linlock, and so these are 68% confidence intervals as they're constructed by this global search algorithm. So yeah.
But how much, when you do the double difference, how much do the locations move? And how do you preserve the absolute information?
So the idea here is that the centroid of any cluster of events should not move if it's relatively accurate. So let me say this. If the arrival time observations have random errors associated with them, and that's not true, but we can ignore skewness at small cost. If they're randomly distributed, then we would expect them to increase the diffusivity of a cloud of earthquake locations, not in part a systematic shift. And so if the absolute centroid is correct in an absolute sense, and then we relocate all the events within that cluster relative to that centroid, then they also should be absolutely correct.
And how much do they move compared to these other numbers?
Less than a kilometer, typically. So I haven't, I don't have a good answer for that, but less than a kilometer. Okay, so here is a timeline showing the number of events in the catalog in 1 year bins in the top panel and 1 week bins in the bottom panel. Gray bars show the number of events in the SCSN catalog, and the black bars show the number of events in the in our catalog. So the first thing to note here is that indeed we detect and locate more events than the SCSN catalog, as we expected. In the bottom panel, I'm also showing significant events, magnitude 3.5 and greater, as stars, scaled according to the vertical axis on the right-hand side. And the 3 largest events during the analyzed period are indicated by these 3 red stars. You'll notice that each red star is accompanied by a spike in the event detection rates, which we would expect based on typical main shock aftershock sequences. But you'll also notice that there are a couple spikes here that are uncorrelated with any main shock event. So we visually review these sequences and confirm that they're event swarms. So these are periods of heightened seismic activity that don't follow the typical main shock aftershock statistics.
So your data set, like your number of stations are keep increasing over these years. So
Yeah.
this is also like magnitude completeness is changing, right?
Yeah, so that's definitely affecting this. And you can see sort of in 2010, starting in 2010, we on average have greater a number of earthquakes than prior
So
to
right now,
2010.
all that kind of changes are included in this.
Yes, yeah. Okay, this is a slide making a similar point. We look at the magnitude of catalog completeness for our catalog and the Hodgson et al. Catalog. And we see that inside our focus region, our catalog is nominally complete above 0.5 to 0.6, magnitude 0.5 to 0.6, whereas the Hodgson et al. Catalog is complete above about 1. Outside the focus region, however, the Hodgson catalog remains more complete than ours. So this work is really complementary to the Hodgson et al. Catalog. It provides more detailed coverage during a limited time period in a limited spatial region. So this remains the standard catalog for regional seismicity in Southern California. Okay, so what do we see in this seismicity? This is a surface trace of a vertical transect running from northwest to southeast. And this is what it looks like if we project all seismicity within 15 kilometers of the fault onto a vertical plane. I've color-coded these by time, by origin time. And we've interpreted a few different regions based on characteristic seismicity patterns. I've labeled them regions 1, 2, 3, and 4. Region 1 is missing the label because it's just a little bit small. So region 1 is just the uppermost 1 kilometer, and it's defined by the absence of seismicity. The same thing is characteristic of region 4. So region 4 we interpret to be void of seismicity because the rock is hot and under high pressure, so it deforms in a ductile manner. Region 1 we interpret as not being truly devoid of seismicity, but having low brittle strength because of low confining pressure, and therefore unable to sustain the elastic strain energy that's needed to nucleate earthquakes of detectable magnitudes. In region 2, seismicity is characterized by dense clusters of uniformly colored points. So this indicates that they're both spatially and temporally clustered. In region 3, however, we have fairly uniform distribution of colors, indicating that these events are temporally diffuse, and they're also spatially diffuse compared to the overlying region 2 seismicity. So we interpret this region 3 to be the brittle to ductile transition zone, and region 2 above to be the brittle regime. In the top, I've indicated the extent of the hot springs area, the Anza seismic gap, and the trifurcation area. And you'll see that in the hot springs area, seismicity is primarily located in the brittle to ductile transition zone. The northwest extension of this transition zone beyond hot springs is not evident in our catalog. And region 2 seismicity in hot springs is relatively sparse. Here in the Anza seismic gap, there is an absence of seismicity that penetrates all the way through the brittle to ductile transition zone there is some seismicity on the northwest edge of the transition zone, but outside of the outside of that seismic gap on either side, there is a absence of seismicity in the brittle to ductile transition zone. Trifurcation area seismicity is chiefly in region 2, and so this is the most productive portion of the San Jacinto fault zone, and also Southern California by extension. So based on a typical rock strength profile, we would expect the largest events to nucleate near the bottom of region 2, the bottom of the brittle zone, and these stars indicate the largest events. So there's actually 2 stars here, a white one and a red one just behind it, and those are the 2 largest events that nucleated during our analyzed period, and indeed they're within 2 kilometers of the base of the brittle zone.
Your hot springs area, I'm puzzled by, because normally I would think of an area as hot.
Mm-hmm.
The brittle ductile transition would be shallower.
Yeah.
So what you're seeing is opposite. So that means either my understanding of the hot springs is wrong, or there's something else going on there.
Yeah. I mean, the name hot springs implies hot, but I guess we would have to look at some heat flow data to actually say whether or not it's hot. And off the top of my head, I don't know.
Okay, there must be heat flow data from that.
Yeah, there is, and I don't have the answer. It's also possible that there's some basement lithology that's controlling this feature. Because, we see it dip down, and we see this downwards bulge, and that could potentially be explained by mineral composition with different melting temperature than we see in the trifurcation area.
Are there hot springs in that area?
So to the southwest, there are, so between the San Jacinto and the Elsinore faults,
so it's not
there are some. Yeah.
So at the hot spring area, like you have a lot of earthquakes in the brittle ductile transition zone. And, I understand the ductile zone is fine, but how they release the stress on the brittle zone, because there are no events, and it looks like there are stress accumulating during the event. So,
Sorry, I don't think I got the question.
So during the event, you have a lot of events.
Yeah.
The stress on the edge
Mm-hmm.
should be accumulating over the years.
At the upper boundary here.
Upper boundaries.
Yeah.
And they have to release the stress.
Mm-hmm.
And usually that is earthquakes. But,
Yeah.
Obviously there are no events. So
Yeah.
how they release the stress?
So there is a publication in 2018 suggesting that there's deep creep on the northern section of the San Jacinto. So perhaps that is relieving the stress here. It's being released through slow slip. That's a possible explanation, but I can't say. Okay, so that is the fault parallel transect, and so now I'll show you one running from southwest to northeast through the hot springs area. And again, we see that the seismicity is primarily located in region 3. I'm showing the vertical projection of the Clark fault and the hot springs fault here. And you can see that again, the seismicity lies primarily between the surface traces of the faults. They form sort of these limbs of diffuse seismicity that converge at low angles near the top of region 2, where seismicity rapidly decreases. There is some region 2 seismicity about 10 kilometers to the southwest of the Clark trace, but by and large, the majority of the seismicity is here in this brittle to ductile transition zone.
Is there geologic evidence that the faults really are vertical, or is there any geologic evidence of dips?
There is seismological evidence of dip, but geological evidence of dip, I think that's an open question. Okay. The understanding that I'm aware of right now is that the faults are assumed to be near vertical, near the surface, and the dip shallows below about 10 kilometers. And we can kind of see this in the next section from C to C prime through the trifurcation area. So here we see a great number of discrete surfaces. So these are highly localized surfaces that have nearly vertical dips, but below about 10 kilometers. I'm not sure how clear it is on the projector here. Yeah, it's kind of hard to make out on the projector, but the dip, if you squint just right, you can see that it does tend to shallow, and there's some other people who have suggested that below 10 kilometers it does indeed shallow. The seismicity here is distributed on these discrete surfaces which converge to this sort of 10-kilometer wide swath of diffuse seismicity in the brittle to ductile transition zone. Now, so we're looking along the fault here, and so we expect to see the edges of fault surfaces, but we're also seeing the broadside of a few structures here. And so if we look at those in map view, you can see that there's actually these sets of conjugate surfaces, particularly in the shallow crust here. So in the previous slide, this yellow and this red cluster, we're looking at the broadside of these structures here. So the seismicity that is trending orthogonal to the primary fault trace is distributed in these conjugate structures. And then again, we have the deep seismicity located primarily between the Clark and the Buck Ridge faults. Okay, so this slide is looking at some similar events. So what we do is we apply a simple chaining rule to link similar events, where if event A is similar to event B, and event B is similar to event C, then event A and event C are indirectly similar. So we assess similarity by taking our cross-correlation data from earlier for P and S waves and asking, are there at least 5 stations that have cross-correlation coefficients greater than some threshold? So I'm showing a threshold of 0.9 here and 0.8 in the right column. Waveforms are shown in the top row, and bottom row shows the locations of the events producing those waveforms. So I've sorted these waveforms based on the cross-correlation with a template event, which I've labeled with a red star in the map, and I've color-coded the events producing these waveforms by their correlation with that template event. So for a relatively high correlation coefficient, we get we get 721 events that are considered similar, and the waveforms across the gather are largely coherent.
Are this done on vertical components?
So when we cross-correlate the data, we actually we correlate all 3 components. So vertical with vertical, north with north, east with east. And we do that for P waves and for S waves.
And the waveform is?
Oh, sorry, yes, the waveform, these waveforms are all P wave waveforms on vertical component data, yeah. And so, again, this is kind of small, and I apologize for that, but the seismicity in this gather is actually distributed along conjugate surfaces. And so the interesting thing here to me is that events on conjugate surfaces produce similar waveforms, provided that they are relatively close to one another. If we lower the threshold by a fairly modest amount to 0.8, the number of events that are considered similar increases to over 3,000. These events span over a distance of over 10 kilometers and all 3 major faults in the Trifurcation area. So again, so the trace index 0 represents the template trace, and trace index 3000 here indicates the least similar trace to the template. And so we can see in this plot that the waveforms are not coherent across the entire gather. And so this implies that there are dissimilar events that are linked by continuous chains of similar events. So it's kind of a gradual change in waveform character from the template event to the events on separate faults.
So point 8 is the entire waveforms you show, or just
So event A is similar to event B with minimum 0.8 threshold, and event B is similar to event C with the same threshold.
and that is calculated in that 1.25?
Yeah. But event A and C need not satisfy the similarity criteria. So there's a continuous chain of similar events that link ultimately dissimilar events. And so to me, that suggests that using a recursive or adaptive template matching technique, like William Frank and Rachel Abercrombie did here in New England, might be particularly well suited to a fault zone like the San Jacinto. So on something like the San Andreas, which is much more mature and we would expect less diversity of waveforms, such a method might not be as well suited. But for something younger and more immature like the San Jacinto, a method like that might work quite well.
Am
Yeah.
I reading correctly, the upper left panel is the bottom 700 and the upper right panel? So I'm looking at the waveforms. That's
Yeah, yes.
700 waveforms, are those the first 700 on the threshold 0.8 panel?
So yes, they are.
And they're ordered by how correlated they are.
With
so
the template
it should be
trees.
the first 700.
Exactly. Yeah.
Because you can see pattern, and it's a little harder to see it, that emerges in terms of the coda event is sharp in the first 700 and then it becomes diffuse.
Yeah. And this sort of secondary or tertiary
Clear on the
impulse here
left,
is,
but it's broadening
yeah.
and then disappearing.
But this highest amplitude signal is coherent across the entire gather, which implies that there might be a unifying process that is, unifying these different events. So there's second order waveform characteristics that are muddying things up, but there may be an underlying similarity that can be extracted.
And do the distances tell a story?
Probably, but I don't know what it is.
Okay.
So how can I interpret that main part is main wavelet is very similar over 3000, even that is quite
This-
far? Like structure in heterogeneity along these two paths is kind of similar?
So I would guess that to the first order, I mean, they're all right lateral strike slip faults in a similar geological context. The path effects from each of these is going to be different, but this might be sort of the signature of a right lateral strike slip fault in the San Jacinto fault zone. And then all the different paths add the secondary waveform characteristics. That's kind of the way that I'm understanding it right now. And so, one thought is maybe by running a principal component analysis on this, we can extract the component that is truly similar, and that might give us a keen insight into fault zone dynamics, the regional unifying processes in the fault zone. Okay, so this is some of the work that we've done so far, so I just want to touch briefly on some what I think are interesting questions and directions to keep working. One question is the ANZA seismic gap. Is it locked or creeping? Why is there why is it relatively devoid of seismicity? Is it because it's storing elastic strain energy, or is it because it's slowly releasing it? The northwest extension of the brittle to ductile transition zone beyond the hot springs is interesting. There's in the literature suggestions that there's deep creep there, and so how does that relate to the seismicity structures that we're seeing? And then what is controlling the hot springs bulge, I'm calling it here? Is that indeed controlled by basement lithology? Is it primarily a heat signature? What exactly is controlling this bulge? Ways to try and get at some of those questions are to do some further analysis of the seismicity patterns of the catalog that we now have. So I've shown the catalog and I've presented some preliminary interpretations of the patterns that we see, but there's presumably a lot more embedded in this catalog that we can dig out. I've seen some videos of laboratory experiments where they subject a rock sample to high stress and they record acoustic emissions that show a progressive localization preceding catastrophic failure. And so one interesting question would be, do we see a similar sort of thing in the wild? Are there similar signatures in real fault zones? The catalog right now goes through the end of 2016. Some of the key stations from the San Jacinto Fault Zone Experiment Network continue to operate, and so a logical extension is just to continue the processing through the end of 2018, and I mean through present ultimately, and so that's kind of a data-driven component of further research. We have lots of information on seismicity patterns, but we can get a lot more of information about fault zone geometry by deriving focal mechanisms for the catalog. And that's made challenging by the fact that microseismic events have low signal-to-noise ratio, and so measuring the first motion polarity is challenging, but that's something that we're beginning to work on now. I alluded to the idea of template matching, so we can increase. We've seen increases of catalog size by an order of magnitude, and so by applying template matching techniques, we can expect to achieve similar results for our catalog. And then finally, we can do some tomographic imaging using this updated catalog. And so I'll just show you quickly some preliminary results that Hongjian and I have been getting using this catalog. And so I'm showing P-wave velocity structure and S-wave velocity structure with seismicity as gray dots. And you can see a really striking correspondence between these high velocity zones and seismicity. Also this low velocity zone in the Anza seismic gap, and a similar feature here to the northwest. So one question is, are the processes that are active here also active in the hot springs area? And what does that imply for future large earthquakes and the physics of those large earthquakes? So I'll just leave you with the key takeaways. So if you remember nothing but these key points, I'll be quite happy. We've developed an automated processing procedure to derive an earthquake catalog from raw waveform data. So you can go into a brand new field area with a fresh deployment, and you can apply this processing procedure and end up with a catalog of earthquake locations and magnitudes. And it's a high quality catalog. You know, this is comparable in its nature to the standard regional catalog in Southern California. It actually even is superior to it in some regards. So we take this automated processing procedure that we've developed and derive a new catalog in the San Jacinto Fault Zone with 108,000 earthquakes between 2008 and 2016. And we can begin to look at these the seismicity patterns embedded in this catalog to interpret mechanically distinct regions within the fault zone and the implications that they bear on the maximum likely rupture dimensions and earthquake physics. So with that, I'll thank you for your time, and if you're interested in anything more, this paper's now in review, and if you want the catalog to play with it or look at it, I'm happy to give it to you. So thank you all for coming to listen today.
Very interesting talk. We have time for a couple of questions.
Thank you for the interesting talk. I have a question on the slide number 32, or the conjugate pattern of the rotation of the events. Yes, here, so do you have any idea about the regional stress, like the orientation of the principal stress of this region? And is it corresponding to the orientation of the failure plane?
Short answer is no.
Right.
But such information does exist. It's an interesting question to look at, but I don't have the answer off the top of my head.
Yeah, quite interested in this stress region because when you invert the focal mechanism of the rotation on the conjugate plane of this rotation, and if the sense of the slip is corresponding to the regional slip, and then it's a strong gradient that the regional stress is well controlled the rotation landscape.
Yeah. Yeah, so by deriving the corresponding focal mechanisms for all these events, we can start to get, I think, an accurate understanding of the answer to that question. There is some work that's been done already in that vein, looking at stress inversions from existing catalogs, but with a more complete, more detailed catalog, we can get a better understanding.
Yeah. Thank you.
Do the events in the brittle ductile transition have some characteristics that are different from the shallower events in terms of frequency or?
In terms of waveform character, they do in terms of magnitude. So the brittle to ductile transition zone has, I think, 4 events that are greater than magnitude 3.5 and none that are greater than magnitude 4. And they all occur in the hot springs area. All of the magnitude 4 and greater earthquakes are in the brittle zone. Based on just general waveform characteristics from hot and soft areas like mid-oceanic spreading ridges compared to cold and brittle regions like subduction zones, I would assume that they do have different waveforms, but I haven't done a systematic look at that in particular.
Thanks.
Other questions?
So I just want to make sure I got this correctly. So you're defining your brittle to ductile region, because I thought you defined your brittle to ductile region as, oh, well, the strongest earthquakes happen right at the base of the brittle region, and that's how you define the start of your brittle to ductile transition region. So isn't it kind of a bit circular to overinterpret the brittle to ductile region because you're kind of defining it qualitatively that, oh, we think this is it?
So the way that we've interpreted these regions is based on the spatiotemporal distribution of seismicity, not looking at the size statistics, so not looking at the magnitude statistics. It happens that the largest events are at the base of region 2. But it's, so the main thing that we're looking at, and this is admittedly quite qualitative, it'd be interesting to try and quantify it, but we see these dense clusters of uniformly colored points in region 2, and we see spatially diffuse, randomly colored points in region 3.
Thank you.
Any other questions?
Quick question. So you talk about the temporal and spatial distribution within the brittle ductile transition. How about the moment, distribution moment? Are they also randomly distributed, or are they have some coherent patterns?
Sorry, the what moment?
So you got the magnitudes, right? Sorry, the magnitudes.
Yeah.
Magnitudes is also randomly distributed, or is it some coherent patterns inside of brittle ductile transition zones?
So there is a coherent pattern in the statement that I made that there are no magnitude 4 and greater earthquakes in the brittle to ductile transition zone, but the say like the B value of earthquakes in this zone, it may be different than in the brittle zone, but again, that's an analysis I haven't done, so I can't answer that.
Okay, and then let's thank our speaker again.